So this session I'm going to talk about cryptography pitfalls. As I was introduced, my name is John Downey. Turn my clicker on. I work at a company called Braintree. If you haven't heard of Braintree, Braintree helps businesses process payments for e-commerce and mobile payments. At Braintree, I work on the security specifically, which has kind of given me the insight into the cryptography part and specifically the pitfalls that we sometimes see. And one thing that, if you don't know anything about Braintree, Braintree was acquired by PayPal just about 2 years ago. So don't trade PayPal based on what I say. A few other kind of warnings and caveats in there. But to introduce myself, I live in Chicago. This is actually my first time ever coming to Canada. And it's basically what I had imagined. There's like a Tim Hortons on like every other corner. Everybody was really friendly. So thank you to people in Toronto for making my first trip to Canada meet my expectations. So we're first going to start with an overview of like what is modern cryptography. When we talk about cryptography in the modern sense, what do we mean? And then we're going to talk about the common pitfalls and the misses. And I'm interested specifically in how I can help developers not fall into these same pitfalls. You know, this isn't meant to be like kind of a highly prescriptive talk where you can walk away from this and know everything. It's kind of meant to clue you into, I'm in this specific area. Someone has had an issue with this before. Maybe I should like go learn more instead of like trying to build it myself. That's kind of my goal. My goal is not to teach you how to do it correctly. It's to scare you into recognizing the areas where you are probably going to screw it up and hoping that you get help with those. So in the modern sense, we talk about cryptography in 3 different purposes. The first one is confidentiality. So this is what we commonly think of when we think of cryptography. If I'm going to send a message from myself to one of you, my intention is that no one else who intercepts that message should be able to read it. We have the confidentiality that the communication is just between us. In crypto, this is the encryption part. Another part that we associate with cryptography in the modern sense is authentication. When I'm sending a message to one of you, we want to make sure that no one has been able to modify that message since I sent it, or at least in a way that we can't detect. So if they modify it, we should be able to detect that they've modified it. And then the last one is identification. We often want cryptography to help us identify who is the person we're talking to, what server are we talking to. Am I talking to the real PayPal.com? I want the extra assurances of that before I give them my PayPal username and password. We often combine this with the previous one, authentication, in the form of digital signatures. So you get both. You get John sent this message and it hasn't been modified since John sent it. Cryptography is a rigorous science. And what we mean by this is that it's peer-reviewed. It's based on hard math problems generally. For example, the RSA is a really common algorithm that you may have heard about. RSA is based on the factoring problem. So we have gigantic numbers and we want to factor them into their base primes. That's actually really hard to do on classical computers. So what I mean when I say classical computer is I mean everything that's not a quantum computer. So like all the computers sitting here in the audience. So it actually is efficient to factor numbers on quantum computers. Unfortunately, we've only been able to build a quantum computer that's big enough to factor 21. So still a ways away from it being dangerous to RSA. And what we're betting on now with cryptography is that there's no major advances in either math or computers. So we're betting on those two for right now. And these are math problems that we've kind of thought a lot about. And we're like, wow, this is going to be really hard for a while, 20, 30, 40 years. As I mentioned, cryptography should be peer-reviewed. This kind of falls into the common advice of like, don't invent your own cryptography, don't design your own cryptography. All of those are kind of stem from this. You don't have the resources to get it properly peer-reviewed. And to kind of go along with this is there are a lot of peer-reviewed cryptography schemes out there. The kind of flip side that isn't as often talked about is don't try to go implement those yourself. So you may have all the test vectors for AES, and you give a programmer like test cases, they can go like try to whip up code that meets those test cases. but you're often going to overlook a lot of like really subtle problems around timing and cache invalidation in the processor that unfortunately will totally break your system and leak data, especially if you're operating like a cloud environment where you're technically sharing processors with other users. And then the last part of this is something called Kirchhoff's principle. So the only thing that should be secret about your crypto system are the keys. I should be able to publish a design white paper of exactly how our data is encrypted, and that should remain secure because I haven't given you the keys. You shouldn't be relying on the security through obscurity. So cryptography itself is very strong. Individual primitives like AES and RSA, they themselves, you're not going to attack them directly. I don't expect to wake up tomorrow and read the headline, AES is broken, just totally broken. I do expect to wake up and read the headline, some way in which you combine AES and Diffie-Hellman and RSA together is broken because there was a mistake made 20 years ago and we haven't gone back and fixed it. And those actually come up from time to time, things like Poodle and Breach, or Poodle more so than those, and then Logjam, stuff like that. So systems built around cryptography are only as strong as kind of the weakest link, so they can tend to be fragile if they're not well thought out. And unfortunately, the missteps are often catastrophic. So in the case of Heartbleed, it wasn't the algorithms that were the problem, it was an implementation of how one part of TLS was done. And because of that, we had to go and basically rekey a good chunk of the internet, which is not an easy step to do. I'm going to read this for you real quick, and it kind of drives home a point that I really liked from this book. So this is from the book Cryptography Engineering by a couple of really well-respected cryptographers. You have probably seen the door to a bank vault, at least in the movies. You know, 10-inch thick, hardened steel with huge bolts to lock it in place. It certainly looks impressive. We often find the digital equivalent of such a vault door installed in a tent. The people around it standing around arguing over how thick the door should be rather than spending their time looking at the tent. So you'll often see this come up when folks on mailing lists will argue over key sizes or like salting and things like that. They'll be like, well, this needs to be a 128-bit key. No, it needs to be a 256-bit key. And they're often applying these systems to, applying this on top of a system that has like a trivial SQL injection or something like that. So they're focusing on the wrong parts of the cryptography and like not actually realizing that their system has other problems. Cryptographers like to kind of get in and argue about the minutia. And so if you take nothing away from my talk, the basic premise is the recommended way to do this is if you have data in transit, use TLS. We used to call it SSL. We don't actually use SSL anymore, or you shouldn't be. We use TLS or SSH or VPN and IPsec. So that's data going over the wire. That's data in transit. If we're having data stay at rest, so this is on S3 on some hard drive somewhere, for those PGP or GPG, run it through that. Keep the keys safe, in a recommended way, and like that's how you should be encrypting your data at rest. If it doesn't fit into one of these two modes, try to adjust it a little bit until it can, and you'll save yourself a lot of the headaches that come down the line that we're going to talk about. So another thing to kind of highlight is this problem I see over and over, which is when you give developers low-level libraries. So these are things like OpenSSL, PyCrypto in Python, and like Bouncy Castle in Java. And then they're like similar things for like the .NET crypto APIs. I describe it as you're giving developers a bucket of razor blades and you're asking them to build a saw. And you'll be kind of horrified with what happens in the end, and it won't operate anything like a saw generally. So what I want developers to use are high-level libraries. These are things like, so that's pronounced SALT, it looks like NaCl, and libsodium. This is a library from Daniel Bernstein, who's a very well-respected cryptographer, has bindings in C and Ruby and all the various languages. And libsodium and Kezar, which is another library, this one's from Google, they offer a high-level interface that is generally harder to screw up. There are certainly still the rough edges, but you're given kind of a much more functional place to start. You're not asked to pick all these different primitives yourself. often we find that if you go in and the developer is trying to pick like what bit length of AES to use and what mode on AES to use, like you're already way too low level, and that's where problems start to arise. So I promised some pitfalls. So these are, we're going to talk about places where crypto has gone wrong and where developers have commonly screwed it up. This is either they screwed it up or someone that they've trusted down the line has screwed it up. The first topic to talk about is random number generation. So we use randomness as a central part of any crypto system. It's used to generate our encryption keys, API keys, password reset tokens. All these various things rely on the data or rely on the basic random number generator being strong and being unpredictable in a cryptography sense, which is not the same as a statistical sense, like what you would use for a Monte Carlo simulation. The pitfalls we see here, the first one is not using a crypto strong random number generator when you should. This is a paper that was published probably 5 years ago, I think, at this point. It was presented at Usenix, which is a conference, and the paper was I Forgot Your Password, using randomness attacks against PHP applications. So what happened in this case was they found example PHP applications where they went in and they were able to predict the password reset token that was going to be sent to the user before the email was sent. And therefore, they were able to then reset the user's password because they knew what the password reset token was going to be. This was because these applications did not use a cryptographically strong random number generator. So for those of you who are more directly on, you'll be able to see this better than for those of the side, so I apologize. You can check out the slides later. The image on the left has a pattern to it. Like there's a little bit of a wavy pattern to it, and that's because that image was generated using a horribly broken random number generator. I actually kneecapped it as much as I could. It's like the random number generator that shipped with like PHP 4 that only was active on Windows NT and like all these things. So it's as bad as it could be, and it kind of demonstrates what you don't want, which is this pattern. You don't want this repetition in your numbers. The image on the right is like dev random on Linux dumped out and like shown as an image. So it should be cryptographically strong random data. And that's just to kind of demonstrate visually what you don't want. The next one that we see, broken random number generators. So this has bit a few different companies a few different ways. One from a while back was in Debian. So Debian shipped in, I believe it was 2006, a version of OpenSSL that had this line commented out. And what this line did was it mixed in random data from the operating system into OpenSSL's random number generator. It was commented out in two places in Debian, and if you don't know much about Linux, Debian is kind of a seed distribution for a lot of other distributions, so like Ubuntu and Knoppix and all these other distributions picked up their changes and shipped them for a number of years. And it was not discovered until 2008. So for roughly 2 years on these shipping systems, anything that used OpenSSL for random number generation was hopelessly broken. To the point where you can actually, there are tools that will just go enumerate all the possibilities of the start state of the random number generator and like generate all the SSL keys and stuff that could have come from it. So now your vulnerability scanners will go and check this for you. The point of this is that it took 2 years, and the reason is that bad cryptography looks a lot like good cryptography. So you don't, you're like, well, it looks random, so yeah, it probably is. And it takes 2 years to notice. This was the commit message, so it's don't add uninitialized data to the random number generator. This is to stop Valgrind from giving error messages. So if you don't know what Valgrind is, it's a memory debugger tracer for C applications. And it was because someone was getting debugging errors, and so they traced it down to that line, and they commented out and shipped that in Debian. And the unfortunate thing is that they ran this change by the OpenSSL mailing list. They're like, hey, is this cool? And nobody's screamed, oh my God, stop, don't do that. And it got in. So this is that line today. There's these comments above and below basically telling you, oh my God, stop, don't do this. So that's one way to solve it. Another place where bad random number generators popped up this was a few years ago in 2013. the Android phones for a while were shipping with a broken random number generator in the operating system. And the way people noticed is Bitcoin wallets started getting compromised at like an unprecedented rate. And all of them were kind of because they were using these Android Bitcoin apps to send and receive Bitcoins. And due to some faults in the algorithms, if you have bad random number generator, even if you generate your keys not on the Android phone, you can get compromised. So the last one is not using random data when it is required. So this one was a pretty bad one for Sony. So a little background, the ECDSA is the elliptic curve digital signature algorithm. And it has a non-elliptic curve variant called just DSA, or digital signature algorithm. And these are government standards. So one of the requirements of this standard is that you have to input into every signature a random value called K, and that value has to be uniformly 100% random, or if you don't have that, then you can break someone's private key with it, which is what happened for the PS3. Sony was actually using a constant value, I believe. And so you just observe a few signatures, and you can work the algebra back and get their private key. So this was pretty bad. This now allows people to like load their own homebrew on the PS3, which, depending on if you like PS3, is really nice. So recommendations here: if you're on a Unix platform, just read the data from dev-urandom. Just use that. That's the operating system. There's a lot of kind of back and forth on this. I side with the people who are saying just read from dev-urandom. There are of course with every recommendation caveats, but that's generally a good recommendation in my opinion. On Windows, you want to use the random number generator create in .NET, or there's a function in the Win32 API called cryptgenrandom, which just gives you random data from the operating system. Next up, let's talk hash functions. So a hash function is often called a fingerprint, and I think that's a really good way to think about it. It's a one-way identifier that is not reversible. So the point is I cannot just look at a fingerprint and know who it is. I have to have some kind of fingerprint database to do that. And ideally, no two people have the same fingerprint so that we can use it to uniquely identify a person. Some pitfalls here, using weak or old algorithms. So a few years ago, this is actually another good story with PS3s. There was this algorithm a long time ago called MD5. You've probably heard of it. It's still pretty pervasive. And what happened was they've been breaking various parts of MD5 for years up to this point. This was in 2008. And yet people were still using it. Specifically certificate authorities, a few of them were still using MD5. So what this group of researchers did is they pulled together a bunch of PS3s as computing power, which, if you remember anything at the launch, they were pretty powerful for like generic computers you could buy. And they were able to correctly predict the data that would be necessary to get something to match what a CA was going to issue. So what they were able to do is they were able to take the CA signature and apply it to something that they controlled. And what they controlled was a certificate that they created, which allowed them to be a certificate authority. So, and we'll talk about this at the end, but they were able to then chain the trust from that certificate authority. And this was long after you were told to stop using MD5 for any of these operations. And this put the nail in the coffin. Nobody uses MD5 for this anymore, rightfully so. A few years later, there was a different but slight variant on this attack discovered in the Flame malware, which was used to attack industrial control systems in Iran. And this was a previously unknown outside of, so academia did not know about this attack. The previous one, they knew because they developed the paper for it. This one was completely unknown to academia, which leads folks to think that there is an intelligence agency like the NSA or the Mossad or someone involved in creating this, because they required that level of knowledge of cryptography. And then this paper was very recent. So this, they announced what's called a free start collision for SHA-1. So this is sort of what has been putting the nail in the coffin of SHA-1 for a while. If you run a website with TLS, you probably know that there's been a movement to shift your certificates from SHA-1 to SHA-256. All the browsers, after a certain time, will not respect them. So this is a variant of the attack that doesn't like sort of like oh my God, the sky is falling, but it does put some nice numbers and theory around how long until the sky would be falling. All right, so this one's just for fun. This is the logo for, in the United States, our Cyber Command, and they came up with this agency in the mid-2000s. So long after people recommended not to use MD5 anymore. And I know you probably can't read it, but on the inside of the gold ring, there's some letters and digits, and I'll blow it up for you. It looks like this, which looks a heck of a lot like a hash, hex-encoded version of a hash. Specifically, what it is the mission statement of US Cyber Command run through the MD5 function, and then they put it in their logo. So that, I was like, I don't quite get that. Why you would do that? Why you would choose MD5? But that's like cryptography has got to the point where someone who was designing this logo thought this would be a cool Easter egg to put that in there. So the next one we see is misunderstanding what a checksum is. So we often use hash functions to provide a checksum. So we run a file through it, we get a value out, and we think, okay, if the file runs through it again and I get the same value, it hasn't been modified. And you'll often see it in the form of, like, up at the top, there's some files called like MD5 sums and SHA-1 sums and SHA-256 sums, which are just those files ran through that particular function. And the misunderstanding I'm trying to squash here is that folks will download these files and download that and run it through it and get the same checksum and think, good, this file is legitimate, it hasn't been modified. What you should actually be thinking is, good, my download didn't corrupt it. It could have still been modified on the server, and what they did is they would just like run through the SHA-1 sums again and just put the new file upload. There's no digital signature, like a GPG signature on these, so you actually don't know the source or the origin of these the checksums. So just be wary of that. Like, that's not how you should validate the origin of some source code. And then the last one to talk about is something called a length extension attack, which I'm going to kind of try to briefly describe. This is more to like scare you into going and researching what length extension attacks are. Also, if you play the stripe capture the flag, like the very first one, this was the answer to like the last level or the second to last level. If you wanted a hint, it's only been like 4 years. So length extension attacks come about when you have something that looks like this. So often when we talk to an API, we have some kind of API secret key, and then we're going to send some value to them. And we both want to know that that value hasn't been modified in transit. So what we do is we'll run it through some cryptographically secure hash function like SHA-256, and we'll put the secret at the beginning, and then maybe we'll put a pipe or a bar symbol in there, and then we'll pin the data to the back. So this is, so you still see this quite a bit, and this is vulnerable to what's called a length extension attack. And what this lets you do is it lets you append arbitrary data. So if you observe this signature, so I'm able to see it in transit, but I don't know the value, or I know the value, but I don't know the secret, I can append arbitrary data to the end and update that signature. And the way it works is actually very interesting. And when you go and you research it, you'll be like, oh, I can see how they would make that mistake. Like, I would probably program it like that to begin with. And the way you get around this is you use something called HMAC. So HMAC is a hash message authentication code, and it uses SHA-256 in a correct way that is not vulnerable to this length extension attack. Real quick, message authentication code is, so remember back to the uses of crypto that we explained in the beginning. Authentication was that middle one. So I want to know that a value hasn't been modified in transit. A MAC lets you do that, assuming both sides already share a key. So if we've ahead of time set up some key, we can then make sure that without leaking that key, that a value hasn't been modified in transit. It doesn't protect the confidentiality of the data, but it does protect its integrity. So it's often combined with confidentiality. And what you get out is you have a key, a value, and then the authenticator, the value that shows that the other side has the key, is called the tag. So am I telling you this and like nobody actually does this? So Flickr did this in their initial API, and there have been a number of other companies. I actually just saw it the other day in someone's API. And there's a paper that published this, and like this is when length extension attacks first started getting press and notice in the security community, was after this paper. So recommendations, if you need a hash function, like you're like, hey, I need the fingerprint of some data, SHA-256 is a pretty good candidate depending on your use case. If you need a authenticator, HMAC SHA-256. Stop using MD5 and don't use SHA-1 in new projects, and you want to phase it out for places where collision resistance is a requirement. So that's like digital signatures, places like that. Next up, password storage. You're not going to get out of a crypto pitfalls talk without talking about password storage. So in the last few years, there have been a number of companies that have had the unfortunate event of having their user database compromised. So famously, LinkedIn, 8 million, Last.fm 2. Then there was that time Yahoo had something. Dropbox had something that was similar, but it actually ended up being something else. eBay, I was working at PayPal when they were part of eBay at the time this happened, and it was a big deal. Slack also, very recently, this is like last March or so. And in all these cases, the attackers were able to get the hashed or encrypted version of the password. So in not all these cases were they terrible. Like the Slack one was actually pretty good. But in some of these cases, the value, it was like they were trivially storing a very bad password verifier. So this is one that I still occasionally see in older applications, and that is we're going to take someone's password and we're going to run it through SHA-1, and we're going to put that in the database. So this does have value, and there's a reason why they did this, and that is so that it's one way. So a developer running select star on the users table is not going to be able to read that password column. It's not going to be readily usable to them. And then kind of the step up from that you'll see in systems is we're going to prepend a value to the beginning of every password. We're going to call it a salt, and we're going to use it for something called rainbow tables to defend against those. So this is actually catching up to where Unix was state-of-the-art storing passwords in like 1970 something. And yeah, this was like the recommendation in like 2005 for PHP apps. And the value here is that the data going into the hash function is randomized, which means it can defeat these pre-computed tables, which are called hash functions. And it forces the attackers to focus on one specific password in the table that they want. Usually it's like the admin password, to be honest. The problem with this is that hash functions are fast. They're designed to be fast. All their applications they're designed for, they need to be fast. You want your checkout to Amazon to be really fast, or at least Amazon does, because they have data showing that if you wait, you drop off and you don't actually complete that purchase. So everybody wants hash functions to be fast, except for the people using them for password storage. So what you want in a password storage is you want this third property, you want it to be slow, or you want it to be arbitrarily slow. So you want to be adaptive hashing. So this is bcrypt, scrypt, pbkdf2. There's the password hashing competition just finished, and I think theirs was called Argon 2. So any of these are good solutions for it, assuming that you've tuned them correctly. So my recommendation, delegate your authentication if possible. If you're in a business or in a situation where you don't necessarily need usernames and passwords. For example, if I'm signing up to comment on your blog, I shouldn't need to sign up and give you a username and password to comment on your blog. Delegate that to GitHub or somebody. But if you do need to store passwords, store a one-way verifier using bcrypt, scrypt, pbkdf2. I don't really care which one you use, as long as you use one of those and you've tuned it appropriately. So the reason you want it to be slow is that when a user is logging in, they're probably not going to notice an additional half second of their login the very first time. But when an attacker steals your password database, they're going to notice if it takes a half a second for every single guess they have to make of that user's password. It's going to be significantly slower. If you're just using raw SHA-1, they can do billions of guesses a second. So after my talk, occasionally someone will walk up to me and they'll kind of look like this. They'll be like, all right, I know my password storage is bad. It was in a legacy system. It was written 10 years ago. I don't know how to fix it. We don't have time to like go and reset everybody's password and that kind of stuff. It'll be okay. You can fix it. So for example, say we have a password hash column that is just SHA-1 of the salts concatenated with the password. In this case, don't wait for the users to log in and silently upgrade. So this is a solution a lot of developers will come up with. They're like, I'll make a different column, and I'll silently backfill that column as the users upgrade when I get their password in the clear. This has the problem of if your password database is compromised before you're finished with this, they get both the nice hashed version and the trivially broken version. And the reason also with this is that you'd be surprised how often or how long it takes for users to log in, especially in consumer applications. It'll be years, or maybe they'll never log in again. If you're in a consumer application, go look at like a last logged in column in your users table. It's going to be a long time ago. Like we still have some from like 2008 when the product first started. So the solution I recommend is wrap bcrypt around the existing scheme. So your password validation just becomes bcrypt of that SHA-1 thing. Go upgrade them all in place. Just backfill it, write your code to support it, upgrade all the passwords in place. However, this does require that your previous password scheme not be just totally atrociously bad. So like if you were using the DES version of crypt, that's really bad. Like it like concatenated users' passwords to 8 characters, and like uppercase and lowercase didn't matter. Like there's all kinds of reasons why you shouldn't have used that. And in that case, you're better off like forcing a password reset across the whole app. So now your password hash column is bcrypt of SHA-1 of the salt in the password. And you'll do much better in the case your application gets compromised. Hopefully it doesn't, but if it did. All right, so next let's talk a little bit about block ciphers. And this pitfall looks pretty much the same, unfortunately, which is folks are still using old and weak algorithms. This is a paper from a few years ago, breaking ciphers with Copacabana, which is a cost-optimized parallel code breaker. So what this was is, at the time, this was 10,000 US. This was a few years ago. You could build a machine that would break DES encrypted data in like a week. And so now it's probably much, much cheaper in much, much shorter time. And yet, I still will audit code bases occasionally, and I'll see that they're encrypting something with DES. And that's just like, stop, OK, we're going to reprioritize, do that, yeah. It does not include 3DES, which is very, very glad that you pointed that out. I had something in the end to kind of talk about that, but I pulled it out. So I'm glad you brought that up. So 3DES, or triple DES, is a variant of DES, which used DES 3 times, hence the name, in a way that gave you longer keys and a better cipher for the cost of speed. But if you had like hardware optimized stuff, you can have the benefit. So yes, 3DES, still you should probably be on the path to upgrading, but you are in a much better place than those who are just using regular DES. So the next pitfall we see is folks using what's called ECB mode. So really quick to rewind back, what AES or any block cipher like DES or Blowfish, or don't use DES or Blowfish, but if you use like any of these block ciphers, what they are is they're a primitive function that operates over a key, a plain text, and a ciphertext. And these all have fixed values and how long they can be. So in AES specifically, the value can be 128, 192, or 256 bits in key size. Those are what you commonly see those are what you would see for AES, which happen to line up with like confidential, secret, and top secret, or which is what they were going for. And then the plain text and the ciphertext are 128-bit values, hands down, period. If your value is longer than 128 bits, you got a problem. And how do you solve that problem? Well, a lot of programmers will solve it this way. They'll be like, I'll just loop it, and I'll just do 120 bits at a time, so that's 16 bytes, and I'll do the first block, and I'll do the next block, and I'll do the next block, and then in the end, my whole thing will be encrypted. So unfortunately, anything that has structure, that structure is going to shine right through. So this is kind of a trivial, like, hey, look at this. So this is the Braintree logo encrypted with AES 256 super secure ECB mode. And as you can see, you can still tell what the logo is. So you think my data doesn't have structure. Is it like an XML file? Is it like a PDF? Is it a JSON file? All of them have kind of structure that shine through that may leak information. So what you want is something that looks like what's on the bottom. And there are a lot of ways to do it. I'm going to give you a couple of recommendations at the end, but just know that ideally what it would look like at the bottom. You have no advantage. You don't see the structure. So the last thing here is not using what's called authenticated encryption. So this practical padding Oracle attacks paper came out a few years ago in 2010, and this is actually what led to what we call the beast attack on TLS. If you're familiar with TLS attacks, you'll know that TLS 1.0 is vulnerable to something called beast, which is a padding Oracle attack that these two researchers found. And they actually were going back to an attack that was found in like 2002 by someone named Serge Vadnais, and they just took his theoretical attack and made it like work, and they like demonstrated it. And that's when people like started freaking out, and there have been all kinds of different remediation recommendations for beast. And so the reason why this is a problem is that they were not properly authenticating the ciphertext. So when you had this, what happens when you have ciphertext, that's something you ran through a AES function. So you have the confidentiality piece, but you don't have the nobody modified this piece. So you just have one of those three things that we talked about. What they found is that you really can't have confidentiality if you don't also have integrity verification. So if I can't validate that nobody's modified the ciphertext, I actually can't validate that we're going to maintain confidentiality of the data. And this paper is one of the first that kind of came along and talked about that. And so this started to really drive a move to what's called authenticated encryption. And unfortunately, when a developer comes to a library to implement AES, like this is PyCrypto, and what you can't really see on just below where it says World of Hurt is all the different recommended cipher modes you can use. So there's our ECB mode that we talked about. There's CBC and a few others, none of which are authenticated encryption modes, by the way. And also up above, like their example is they're using, I think it's Cipher feedback mode. Yeah, so you can't read it because it's grayed out, but they're using CFB mode, which nobody uses in practice, and yet like that's their example. So this is my like first case example of, hey, here's a bucket of razor blades. Hope you don't cut yourself. So recommendations, prefer to use the box or secret box mechanisms from Salt and libsodium. So these are authenticated encryption. They do give you both confidentiality and integrity. Stop using DES. That's like I saw DES in the code base and I wasn't triple DES, so I should go back and let my manager know we need to go fix that right now. Stop building your own crypto on top of AES if you can. Unfortunately, like what if someone held a gun to your head and it was like, PCI, use AES, and it's like, what if you have to use AES, which is a legitimate concern in some industries. Don't use ECB mode. Make sure you're using authenticated encryption. So the recommended way here would be use something called GCM mode. That'd be a good first choice. If you can't use GCM mode because of your platform, there's a lot of other options. But even then, you still can mess it up because if you like don't verify the tag first, like you're still like not getting this integrity part, and it's really easy to mess up in a critical way. So hope you're in, hope you have someone on staff who can kind of walk you through this. If you don't, there are plenty of companies who can come in and like help audit that code and like put you in the right direction, or try to use my recommendation and just use like libsodium or Kezar, one of those. They'll help you out in a lot better way. All right, so this is another one I see a lot of, which is code not properly validating the TLS connections they make outbound. So when we're writing code, we're often not writing code in isolation anymore. Whether it be we're in a service-oriented architecture and I'm talking to a bunch of internal services, or I have an application that tries to do anything useful, which means I have to talk to the outside world in some way, whether it be like some industry system to pull down data, or like a payment processor if you need to process payments for your like e-commerce store. You're going to be talking to someone on the outside world, and you're most likely talking to them over some kind of HTTPS-based API. And here's where, if you're doing this yourself, you have to make sure that you're properly validating that connection. And here's what I mean by that. So a few years ago, there was a paper published called The Most Dangerous Code in the World. Cryptographers also like hyperbole. And it was about validating certificates in non-browser software. So non-browser software, what they mean by that is all the code that we've written that's not in Firefox or Chrome. So these are when I'm making my call out to a payment processor, or when I'm calling out to an internal microservice. And what they did is they analyzed a bunch of mobile applications. This is another case of non-browser code, and a bunch of libraries, and they kind of documented all the places where they just totally break TLS. And if you were to man in the middle of these, like you were to get in between someone using it and the intended endpoint, you could read it, you could modify it, you can do whatever you want to it. So some of the things they identified was not verifying the certificate chain. So if you don't know what I mean by a certificate chain, when you pop open a HTTPS site with the little green lock icon and you click on it, you can often get to a screen that looks somewhat like this. And up at the top, there's a little tree view that goes from some company that you may have heard of that sounds really trustworthy, like VeriSign, down to the domain you're actually trying to hit. So in this case, it's www.braintreepayments.com, which is my company's website. So this is the certificate chain. This is our site served back a certificate that your browser is able to verify the digital signatures of all the way back up to this VeriSign route, which was either shipped with your operating system or came with your download of Firefox or something like that. Unfortunately, in code, things like this sometimes pop up. So they just tell you to like, oh, I'm going to use curl, just add a -k. It's OK. So -k turns off certificate checking. Or if we're using like a curl library, for some random reason I chose PHP here, we're going to set verify peer to 0. So verify peer is you telling the system, hey, I want to make sure that I know who I'm talking to on the other end. And if you set it to 0, it's not going to. And what this allows an attacker to do is literally serve any certificate. It doesn't matter. It doesn't even have to be valid, and you'll just go through. And so you can trivially man the middle of it. The next one is not verifying the host name. So the reason why you sometimes see this is that host name verification is protocol dependent. So like HTTPS does it different than FTP, does it different than others. So OpenSSL doesn't just give this to you. You're kind of, if you're using raw OpenSSL, you're expected to handle this. And then also, for whatever reason, some people just turn it off. I don't know why curl has this option, but if you set verify host to 0, you're saying, hey, as long as they serve a valid certificate chain, I don't actually care what that certificate chain says. So I can serve my certificate chain from my blog, and I can man in the middle your call out to like some service that you're using. And then the last one is using a broken library. So this one is a little bit out of your control, besides the fact that you have to just monitor for it. So the big one that we all know about is Heartbleed, most likely. If you haven't heard about it, you were not watching CBS like 2 years ago. Like I was in a cab in San Francisco like 8 months after Heartbleed came out, and there was like a screen in the back of the cab talking about Heartbleed on like the local news. And I was like, something from my industry has made it to local news in just like a far-flung place, and it's like, but it was that big. Like it was big enough my dad asked me what it was. So. So another one you may have heard of, it was the go-to fail, which was an Apple-specific one. So this was an iOS and OS X where they weren't validating part of TLS correctly. And these are just ones that you have to just watch for. Like when they pop up, you have to patch and make sure that you stay patched. So my recommendations here, ensure that you're validating your connections. Like go through your code, make sure that you haven't set verify peer to false or anything like that. Often where this kind of sneaks in is folks in development, they'll be like, oh, well, the dev server, we're not going to buy a real certificate for it, so we're going to set up a self-signed certificate, and they'll turn it off, but then that code gets shipped to production without it being fixed. So that's where you'll sometimes see that. If you can, lean on your framework or library that you're using to make these connections, so like curl. But you need to make sure that that thing does the right thing also, which is kind of weird to say, but like AF networking, which is a really popular iOS networking library, has had, I believe, a few HTTPS verification bugs in it. So it's always best to set up some automated tests to validate these settings in your applications. And you can kind of look at what badssl.com does as an example of these. So we, in our code bases, have these tests, automated tests, like integration tests that will spin up a server with a bad certificate and just make sure our connections fail for the reason we expect them to fail. If you are configuring a TLS server and you have no idea what to support and like what ciphers to prioritize and all these things, Mozilla has a really good tool that you can use. I will tweet a link to these slides later. Or you can, I think they're also provided through the conference actually. So you can find these slides later and you can follow this link. Mozilla has this really awesome tool that's like, I use Nginx, or I use Apache, or I use HA proxy. What are the settings I should configure? And can kind of walk you through that. So one of the last things I want to talk about is trust. And there are a few different ways that we have trust in cryptography. We have the root store, the CAs that ship in your computer, and that's like the PKI infrastructure version of trust. There's also this version of trust. So raise your hand if you've seen this kind of message before. This is SSH when you first log into a server. So keep your hand up if you have validated that fingerprint before typing in yes. There's usually one. So what you're saying what SSH is asking you is, hey, my version of trust is called trust on first use. And what that means is that if you validate this for me at first, like a champ, I'm going to be there every time to help you after that. And so you just have to validate it the first time, and they can do it every other time. And the reason is like there's no like root certificates to ship for SSH. But you'll also end up with something like this, which you'll see if the key that you said was true, yes at the beginning, changed, either because the IP address moved to a different server, or you reinstalled the operating system on that server, or re-imaged it or something. And what SSH is doing is telling you, hey, you asked me to tell you if something bad happened. Well, something bad happened. Please help me. And usually, folks take this and they just like delete the entire known host file, which is all those trust pins you've set up, which is even worse because now you just like obliterated your verifications that you've given SSH. So another thing is, and this is incredibly small to make a point, these are the list of certificate authorities that were shipped in Firefox in 2009, so this list is more than doubled probably. And the reason why I show these is one, the presentation software I use doesn't like know how to make columns. But two, it's to kind of show, it's like, wow, there's a lot of companies up here. There's companies you've heard of, like VeriSign and Wells Fargo. But there are companies, there are things up here like the Hong Kong Post Office, the United States Department of Homeland Security. And you're trusting all of them to sign a certificate for any domain out there ever. And I'm not saying you should go delete them, but it is interesting to kind of think about, like, do I trust these organizations? Do I trust their hiring, firing practices, their auditing practices, all these things? And it's just like, think about that for a minute. Not that we have a better model, but just think about it. So there are a few ways you can help with this. One of them is called certificate pinning. So there are a few different ways you can do certificate pinning. There is recently a HTTP header you can add to your website, which is a trust on first use HTTP header, which is where you're like, I want my certificate chain to always look like this. So either I pin some specific roots I trust, or I pin my specific certificate. And sites like Facebook and Google are using this because they actually have nation states who will compromise these companies. Like one in that previous slide is a company, DigiNoider, which was compromised, we believe, by the Iranians. And they did start issuing certs for like Gmail and like tried to intercept people's traffic. And that's why it's Google and Facebook have a vested interest in making sure that at the very least they can detect this. So they can start throwing out warnings and telling the user that something bad's happening. So certificate pinning is one way that you can do that. So I recommend that think about what organizations you really trust, and then investigate whether certificate pinning for your apps makes sense. So that is my presentation. I hope that you're properly scared of cryptography to at least double think when you go and try to implement it, but it is over. Some things you can go and take away and do. If you're interested in crypto, there's an incredibly good Coursera class from Stanford that covers a lot of really awesome things. There's a version 2 that's supposed to have happened. It's like the Bigfoot of Coursera classes. Like someone somewhere heard it's going to be 2 months from now that it's going to start, and it never does. So definitely check that one out. The version 1 of the class is live, and you can go sign up for the various sessions of it. The other one is the Matasano crypto challenges. So this is at cryptopals.com, and these are developer challenges. You can go and write code to break common crypto problems. So a lot of the ones we talked about, and it kind of helps you realize that oh, I can write the code that breaks these. Maybe I should think more about when I'm writing code that implements stuff around this.